Delighted to be here, delighted to present this joint work with Pepe, who I think is joining online, Mikkel, who's here, and Eric, who's also here, on, as Valerie said, local projections of VARs on what we hope is going to be a useful primer for macroeconomists. Okay, so the starting point for this piece, like familiar to everyone in the room, we as macroeconomists often want to learn about impulse responses. That is the causal effects of macro shocks or policy changes on macro outcomes. Now, the two dominant econometric methods to estimating such impulse responses are VARs, going back to Chris Sims's work, as well as local projections, going back to Oscar's work. Now, in this talk, what we kind of want to do is we just want to give kind of a conceptual way of thinking about the trade-offs and the choice between these two methods and offer some practical guidance for how we think they should be leveraged in applied practice. And I want to structure this short piece around kind of three guiding principles or insights. The first one is a population identification point, that LPs and VARs are two estimation methods, have nothing to do with questions of identification in the following strict sense, that every set of economic identifying assumptions you can make, you can implement in a VAR to learn about a macroeconomic shock of interest, you can also make in a local projection, or vice versa. Okay, so instead, the way to kind of think about the trade-offs between the two is in terms of how they exploit a given finite data set to arrive at this common estimate. And for that, they lie on opposite ends of a bias variance trade-off. On the one hand, local projections or very long leg VARs very flexibly estimate the autocovariances of the data horizon by horizon. As a result, they can be quite noisy. On the other hand, short leg VARs estimate the first couple of autocovariances and then parametrically extrapolate from those. It's going to be quite precise, but maybe subject to material biases. Okay, so now for applied practice, the question is how should we navigate in finite samples this bias variance trade-off? For that, you're going to need an objective function. What we're going to say is that if you want robustly correct uncertainty assessments, in a sense that I'll make precise, then LPs are the way to go, in the following strict sense that they do have a high variance cost, but VARs are going to be fine, provably fine if, and only if, they're going to be as noisy and so equivalent with the local projection. So the rest of the talk is I'll just substantiate on these kind of three core ideas. So let me begin with the identification point. And for that, I just want to very quickly recap what LPs and VARs are actually estimating. So let me begin with kind of a simplest canonical version of a local projection. That is just a regression, re-estimated horizon by OLS, where you regress some outcome of interest Y, H periods from now, on some impulse variable of interest X, perhaps some contemporaneous controls R, as well as a bunch of further lagged controls W that subsume the lagged X's, R's, Y's, maybe some additional variables Q. Okay, so what does this regression estimate? Let's first of all figure that out. Well, that's pretty simple OLS algebra. First of all, what's the shock that you're isolating? Well, if you look at the right-hand side, do the kind of conventional OLS algebra, we see that the shock, which I'm going to call xt tilde, is simply X, but controlling for or projecting out the contemporaneous R's as well as the lag W's. So that's the thing whose effects you want to estimate. And how do you then do this? How do you get at those projections? Well, you re-estimate them horizon by horizon. You run a new regression for each horizon H. Okay, this is entirely reduced form. I have said nothing about whether the object of interest, the coefficient on the X, is actually in any way economically interesting. Whether it's interesting or not depends on the economic identifying assumptions you're willing to make. Okay, so two simple canonical examples would be maybe through some institutional knowledge, you've already isolated a shock, and X is that shock. That's the easiest case. Maybe a little bit more involved, XT is a policy instrument, and the contemporaneous R's as well as the lag W's are the variables that you think enter the policy rule. So you've controlled for the policymaker information set, and then you deal with a simultaneity problem via kind of contemporaneous timing restrictions. That's the canonical Cristiano-Eichmann-Evans monetary policy shock identification approach. There are many other approaches to shock identification. I'll return to those in a minute. But this is kind of a simple canonical LP. Now let's go to VARs. Well, a VAR is a reduced form VAR is a multivariate dynamic model where you relate the W's to their own lags. In this case here, P lags, okay? And then you have some reduced form innovations to use. To turn this system into impulse responses, what you do is you orthogonalize the U's in some way and propagate them forward through the reduced form VAR system. One very simple, familiar canonical approach to doing that is what's known as a recursive ordering, a Cholesky decomposition, where you kind of order the variables W in some particular order. Here, let's say again, R, X, Y, and Q. And then you orthogonalize the U's in that way. Like your first shock is the actual first reduced form innovation U1. The second shock is the second innovation U2, but residualizing out, controlling for the first innovation. And you proceed like this recursively. Now, what does this estimate? Oh, and finally, like the IRFs of interest are then just you have that shock, you propagate it forward via the reduced form VAR. Now, what does that estimate? Let's play the same game as before. What's the shock and how do you do the projection? Well, first of all, the shock, by how I've just described it, is just the residual in a projection of the residual for variable X in that reduced form VAR, controlling for the first NR residuals, the one at the beginning. But if you think through what that is, well, the U's are already controlling for the lag W's. By projecting on UR, you're kind of controlling for the contemporaneous realizations of the R variables. That's just xt tilde. That's the same thing as before in the local projection. Okay, so the shock is the same, but then there's a slight difference. You're not redoing the projection horizon by horizon. What you're instead doing is you're projecting this forward through the reduced form VAR. Okay, that VAR matches the first P autocovariances of the data, but then parametrically extrapolates. Okay, good. So now we have a kind of a basic understanding of what these two methods are doing. Let's now dig a little bit deeper and substantiate the first claim of kind of my identification point. So for this, I want to think through for now a very large sample size. So we forget for a second about estimation and inference. And as a result, let's for a second contemplate P equal to infinity, lots and lots of lags. Well, then, first of all, I've already said it's the same shock that these two things are projecting on. Number two, if you have infinitely many lags, the VAR matches all autocovariances of the data. Projections are a function of autocovariances. Okay, so then it does the same as a horizon by horizon projection. Okay, so same IRFs as the local projection. That doesn't rely at all on the underlying DGP being linear. In very general form, is nonlinear. This is just simple projection algebra. And here's a visual illustration in some underlying DGP that I've made up, where you just see, well, the blue and red lines are on top of each other for P equal to infinity. Now let's make P short. What happens? So finite. What happens in that case? Well, you should still have the same IRF on impact, because again, I said it's the same shock you're projecting on. But now the VAR, as you go forward, extrapolates parametrically. Okay, well, the local projection redoes the projection horizon by horizon. What you can actually show is that for impulse response horizons H that are below P, the two are still going to be at least approximately equivalent in a sense that's made precise in the paper. After that, they can diverge. And here's just a visual representation. P equal to 1, the gray line is that horizon. And now you move that forward and you see the red and the blue kind of on top of each other more or less until then. Afterwards can diverge. Now I push this out and I go to the population limit from before. Okay, so far so good. Now let me kind of culminate into my identification point here. Everything I've said so far was about these recursive orderings. Okay, you observe the shock or you have a simple recursive identification scheme. None of that really hinges on it in the following sense. You can think about more exotic, sometimes referred to as VAR identification schemes, like long-run restrictions, sign restrictions, or identified IVs. In all of those, what you're calling a shock is nothing but sometimes a simple, sometimes a more complicated function of the autocovariance function of the data. And both of these methods are estimating that. Okay, so they have the same estimand. They're trying to recover the same thing. So the way to think about the trade-off between them is not in terms of identification. That's again the first principle. Choice is orthogonal to that. You as an econometrician need to communicate your identifying assumptions first, and then second step is a choice of estimation technique. And so the trade-off is one that's governed by questions of estimation and inference. So that's what points 2 and 3 are going to be about. So let me jump into point 2, the bias variance trade-off. And for that, let me first of all just begin with an observation that will be familiar to many people in this room. If you do run a VAR in a local projection in some finite sample, like you look at the applications in Valerie's handbook chapter, you're going to see at short horizons, they tend to be reasonably similar. At long horizons in particular, they will diverge, with LPs tending to be a lot more jagged, a lot more noisy. Okay? To make a bit more analytical progress on kind of what's going on and how we should think about how these two methods are exploiting a given finite data set, I want to specialize the underlying data generating process to something a little bit more restrictive, but in our assessment, still reasonably general. What I want to look at is a VARMA P0, so with P0 VAR lags, and an MA infinity term that is in a particular sense close to a VAR with P0 lags. So first of all, in what sense close? close in the sense that the MA infinity term is small, in the sense that if you do kind of standard model misspecification tests, it's going to be hard for you to detect this missing MA infinity term. Second observation, in general, kind of a Varma P infinity is a pretty general class. Linearized DSGEs will map into this. Simple forms of dynamic misspecification, like forgetting some variables, forgetting some lags on the VAR side, will all map into this, okay? So it's a general class. At the same time, it's a class that's kind of giving VARs the benefit of the doubt because the MA term is small. We think that's a reasonable starting point because VARs are successful, in particular in terms of forecasting. They provide a reasonably accurate fit to US time series data, but probably don't think the DGP is literally a VAR with P0 lags. Now, what I want to be comparing is two estimators that try to recover IRFs in this general setting. The first one is a VAR with P lags. So that's why I have the P0 here. I want the P to be distinct from and potentially larger than P0. That'll be kind of interesting. And then I look at a lag augmented LP. That's an LP that at least controls for these P0 important lags of variables that are really important via the VAR dynamics, but then may stop there, okay? So how do these two sets of estimation methods compare? Well, here's the one slide result. There's kind of our sense of the bias variance trade-off. These two estimators, the VAR, the LP one, going to be approximately normal with certain means and certain variances. And those terms I want to dig into a little bit more now, where the theta H, what you see here, is the true IRF, the thing that you're actually interested in that's implied by your underlying DGP. So let's begin a little bit with the mean terms. And here I want to stress there's a difference in robustness. The LP estimator is approximately unbiased, even though you're allowing for this general MA infinity misspecification term. That term tells you should be controlling for more lags, but the LP is fine if you only control for P0 lags, because those are the most important predictors, and you're reprojecting on those horizon by horizon. The VAR, on the other hand, is in general asymptotically biased. And here the idea is, I mean, on impact, it's obviously not because they'll be like the LP, but then it's projecting things forward. So it's forgetting some of these important lags, okay, the important predictors, which also suggests that as you increase the lag length of the VAR, that should help. And I'll get to this observation or this intuition in a minute. Second observation, a really straightforward one, the VAR variance is weakly below that of LP just because you're imposing something additional, right? So of course, you've got to be more precise in how you're estimating things. You're not re-estimating horizon by horizon. Now comes the final point on equivalence. Remember how I allowed for P to be distinct from P0. Suppose, first of all, for a second, P was equal to P0. Then you can show that the VAR bias is going to be 0 on impact, but also its variance is going to be identical to LP. They're just going to be equivalent here. Now let me increase P to say P0 plus 1. Then you can show that the VAR bias is actually 0 also at horizon 1. How does that happen? Well, the variance is also identical to the LP variance, okay? And that's a more general principle. If you have P bigger than P0, the VAR is going to be here approximately asymptotically unbiased, but also has the same asymptotic variance as the local projection up until impulse response horizons H that are below P minus P0. And the intuition I've already stressed, LP does things horizon by horizon, the VAR extrapolates, forgets these important predictors, more lags, helps you. Okay. That's a theory. Let's investigate that just a little bit more through simulations to kind of figure out how this trade-off is likely to look in practice. What we've decided to do for that is kind of build off of some of our own prior work, which in turn builds on the work that Mark and co-authors, Mark and Jim have been doing. Where we take as our DGP or start with a large-scale dynamic factor model, which kind of gives us a reasonably good fit to the average behavior of US macroeconomic time series. Slightly augment that to allow for arch innovations to make it even more, even richer, closer to reality. Draw many different combinations of observables from there, of typical macro variables. Implement canonical monetary and fiscal shock identification schemes, and just run LPs and VARs and see how they behave. We contend that at the very least, if you want to use one of those techniques, it should be behaving well in this kind of controlled environment. Because again, we know it provides a reasonable fit to the time series we want to estimate. Okay. So what happens? What I'm going to be doing is I'm going to be presenting results that average across various stationary and non-stationary versions of those DGPs, lots of different observables, different shock identification schemes, and so on, with the fine breakdowns being in the paper. So here's a visual representation. Let me begin again in blue with LPs. Here LPs with different lag lengths, different control vectors that you're selecting. what do you see? On the left, you have bias. On the right, you have standard deviation. On the x-axis, you have the impulse response horizon. And what you kind of see, consistent with what I showed before, tends to be small bias, reasonably large standard deviation that increases with the horizon because you're re-estimating further and further out autocovariances. Now let's put in the red lines, the VARs. Okay. First of all, qualitatively, what you expect to see. Larger bias, smaller variance. It in particular goes to 0 over time because you're parametrically extrapolating and going back to 0. Number 2, here some of these lines are VARs with different lag lengths. Where you see the dark red dashed is a VAR with more lags. And you see at the beginning, it kind of behaves like the local projection as it should. But then once you go beyond the lag length horizon, they start to diverge, exactly as the theory is predicting. Okay? So that's the second kind of broad principle. There's a sharp bias variance trade-off. And I do want to now also point you guys to the y-axis, the magnitudes. The variance cost of LP seems to be quite high. You're paying more than a 1-to-1 cost in terms of standard deviation for the low bias you're achieving. Okay. So now, final thing we need to do is put an objective function, a criterion. How do we, as practitioners, want to trade off bias and variance? Well, here's what we have come up in our most recent work, the criterion we've come up with. It's what we think is a quite natural criterion. It's requiring correct coverage. So by that, I mean is you construct confidence intervals. You say they contain the truth 90% of the time, then they better contain the truth 90% of the time. Given the large uncertainty that we face as applied macroeconomists and the short sample sizes, uncertainty assessments are a really important part of what we're doing. So kind of seems sensible that that's what we want. Problem is, the challenge for VARs is bias is really costly for coverage. So what I'm showing here is on the x-axis, you have the scaled bias of the VAR. So bias relative to its standard deviation. And on the y-axis, you have the coverage. So if you have 0 bias, you have the right coverage. So 95%, 90%, 68%. I just kind of put some conventional values there. The more bias you have, of course, the more you undercover. And you see, even if you have bias of the same order of magnitude as the standard deviation, you can have very material undercoverage. Okay. So now the question is just how much bias is likely in practice. And again, I want to do a bit of theory and a bit of simulations empirics. Let me begin with the theory. I'm going to return to the general Varma P0 infinity setting from before. And it turns out even though that's a quite general setting, you get a very, very sharp answer on what the VAR bias is going to be. Particularly, you can prove that this scaled bias is going to be bounded above by a very simple function. That's just a function of the ratio of the LP and VAR standard errors minus 1, square root of that, times the size of this MA misspecification lag polynomial you're allowing for. 2 things I want to note from that. Number 1, clearly you see the only way for the VAR to be in general fine is for the guy in square roots to be 0, which is the case if the local projection, if the VAR is as noisy as the local projection. Okay, first observation. Second observation is, well, what do we have in practice? What do we kind of tend to see in terms of standard errors? Well, the VARs tend to be a lot more precise. Okay, maybe an order of magnitude of around 2 in terms of ratio of standard errors. You plug that in, and then even if you allow, like, say, these MA lags are quite small, they only account for roughly 1% of the error overall, these missing lagged MA coefficients you're allowing for, you could get a bias that's 1.73 times as big as the standard error. Okay. And from the previous slide, which I'm going to return to now, that would mean very material undercoverage. Final point I want to mention here before I go to the simulations is, well, this was an inequality, but you can prove that this is a sharp bound. You can attain it. You can attain it for some MA polynomial. Okay, that is small, that is hard to detect. So theory doesn't seems a little bit concerning here. Let's see how it actually looks like in practice. Returning to our simulations from before. So what I'm going to be showing here is, yet again, on the x-axis, the impulse response horizon, and on the y-axis, the fraction of DGPs for which the coverage of our confidence intervals is close to our 90% target. Okay? So you want this to be close to 1. You see here LPs do a very good job at short horizons. At long horizons, they also tend to do a good job, but you may need to bootstrap in particular ways, in particular for very persistent, very challenging DGPs, and that's something we elaborate on in the paper. Now look at VARs. Well, kind of see this. The long leg VARs fine at the beginning, then they're going to be materially undercovering. Okay. So that's the third core message. Robust, perfect, 1 minute, right on time. If you want robust uncertainty assessments, the way to do this is via LPs, or equivalently very long leg VARs, much longer than your conventional information criteria would tell you. And you need to bootstrap in particular ways, again, that the paper is precise on. So final thing I want to mention, my last slide, last half minute. So the headline recommendation is to run LPs, as I've said. The paper has a lot of then guidelines on best practice, how you want to do this, okay? And in particular, it stresses the importance of lag augmentation, which I briefly highlighted in the talk here, of bias correction, because the entire point is that you want to minimize bias. And also it has a lot more details on how precisely to construct standard errors, how to bootstrap, and so on. Final thing, what's also in the paper is various intermediate techniques like penalized LPs, Bayesian VARs, and so on. Okay, that's all from my end, right on time. Thank you so much.